Since the birth of the mathematical sciences, humans have used equations to mathematically describe phenomena that they observe in their surroundings. But finding the right equations for describing a phenomenon is not easy, because it requires detailed knowledge about the phenomenon and it often involves a lot of trial and error. So wouldn't it be nice to somehow automate this process? Wouldn't it be nice to have computers deriving equations in the future? Today, the process of deriving equations depends on human creativity. It is not unusual that different scientists propose different equations for describing the same phenomenon. Just to give you one example out of many, both the mathematician Richard von Mises and the engineer Henry Tresca became famous for proposing different mathematical equations that describe how matter is deforming upon external influences. Please don't worry about the details of the equations, I'm just showing this example to illustrate a point. The point is, both equations are physically reasonable, and we cannot tell whether either of these equations is superior to the other, because experiments show that for some materials von Mises' equation and for other materials Tresca's equation appears to be more accurate. The process of deriving equations is rooted in creativity, and it is biased by the individual preferences of the scientists. And therefore there is a current trend in research focused on developing computer algorithms to automate the derivation of equations. In this video you will learn about one of these algorithms, which is called sparse regression. We will consider a simple example for which we will first discuss how conventional regression works, and afterwards we will study in detail how the conventional regression problem must be modified to formulate a sparse regression problem. Finally, at the end of the video, we will shortly talk about a more practical application of sparse regression and discuss some of the limitations of the method. An equation describes the relationship between different quantities or variables. Here are some random examples. Many equations can be brought into a form in which one variable is expressed as a function of all the other variables. Of course, for each of the equations, the function, which I called f here, may take a different form. The point is, if we know how this function looks like, we know how the equation looks like, and therefore, instead of deriving equations, we will focus on deriving functions in this video. To keep things simple and to better visualize the problem, we assume that the function we are interested in takes only one scalar variable x as input. This variable is called the independent variable or the cause. And we assume that the output of the function is another scalar variable y, which we will call the dependent variable or the effect. Most scientific experiments follow the same procedure. We prescribe the cause, conduct an experiment and measure the effect. In this way we can acquire data pairs of x and y. Let's label the data pairs with an index I that goes from 1 to the number of given data pairs and data. Our goal is now to find a function f that describes the relationship between the cause and the measured effect. But this is not our only intention. Yes, we do want the function to describe the data accurately, but, and this is very important, we also want the function to be a simple mathematical expression. Take this function as an example. This function aligns well with the data, but the mathematical expression of the function is unnecessarily complicated. When scientists derive equations, they are interested in finding the simplest equation to describe a phenomenon, because this allows them to interpret the relationship between the cause and the effect. This means we have two objectives. First, the discrepancy between the function and the data should be small. And second, the function should be represented as a simple mathematical expression. Sparse regression is a method that is specifically designed to accomplish these two objectives. So let's see how it works. The starting point of sparse regression is that we assume that the unknown function f of x can be expressed as the sum of some unknown parameters w multiplied by so-called feature functions g of x, where n feature denotes the number of parameters and features. Here is an example with 2 parameters and 2 feature functions. If we tweak the parameters, the function takes different shapes. We can add a lot of parameters and feature functions to the expression to make sure that the function can describe complex relationships between x and y. Here is an example with 6 parameters and 6 feature functions, but technically we can add hundreds or thousands of terms to the expression. The key idea of sparse regression is that we want to calibrate the parameters w in a way that the function aligns well with the data, while at the same time removing dispensable feature functions from the expression in a way that the resulting function takes a simple mathematical form. To understand how this is done, we will take a close look at the simple example with just 2 feature functions, the cosine function and the exponential function. As we said earlier, we have 2 objectives. Mathematical problems in which we want to accomplish 2 objectives simultaneously are often formulated as minimization problems. For each objective, we define a mathematical measure that quantifies in some sense whether the objective is met. This measure should be small if the objective is met and large otherwise. Such a measure is called an objective function, cost function, or loss function. By minimizing the loss function for both objectives simultaneously, we make sure to accomplish both objectives. But how could the loss functions specifically look like for our 2 objectives? Let's take a closer look at the first objective. We want the discrepancy between the function and the data to be small. But how can we mathematically quantify the discrepancy between the function and the data? We need a mathematical measure, which I will denote as L data, that is small when the function is close to the data and large otherwise. Well, we could start by computing the differences between the function values at xi and the data values yi. And we could compute the sum of all these differences. But there's a catch. The differences between f of xi and yi can get negative. This means that this measure can get smaller even if the function diverges from the data. A common remedy to this issue is to compute instead the sum of the squares of the differences between f of xi and yi. Squares cannot get negative, which means that this measure is indeed small if and only if our function is close to the data. And therefore the measure that we have just defined can be taken as the loss function for our first objective. Finally, note that it is common to scale the loss function by the number of data points. But this is just a convention which doesn't really change anything. After having defined the loss function, we can reformulate our first objective in a more mathematical way. We want to find parameters w such that the loss function L data is minimized. Before we start talking about our second objective, let's still focus just on the first objective and compute the parameters w that minimize L data. Recall that the function f is the sum of all parameters w times the feature functions g of x. To find the minimum of the loss function, we compute the partial derivatives of the loss function with respect to the parameters and set these partial derivatives to 0. This is the partial derivative with respect to an arbitrary parameter wk. It looks a bit complicated because of the sums, but what we have arrived at is just a linear equation for the parameters w. As we set the partial derivatives with respect to all parameters to 0, we get one linear equation for each unknown parameter. And we can solve the resulting linear system of equations for the parameters. For our simple example with just 2 parameters, we get this linear system of equations, which we solve for w1 and w2. We can verify this result by plotting the loss function dependent on the 2 parameters. The red dot illustrates the computed minimum. To better illustrate that this is indeed the minimum, let's color code the loss function and plot it in the vicinity of the minimum. Now we can nicely see that we computed the minimum correctly. By minimizing the loss function, we have found parameters w in a way that the function f is close to the data. We have solved a so-called regression problem. Recall that we are considering a simple example with just 2 feature functions. In practice, we don't know upfront which feature functions are good to describe the data, which means that we have to consider much more than just 2 feature functions. Here you can see the solution for the regression problem for 6 feature functions. As you can see, considering more feature functions makes the mathematical expression for the function f more complex. Until now, we have completely ignored our second objective. Our second objective is that we want the function to be represented as a simple mathematical expression. But how can we define the second objective in a more mathematical way? Let's take a look at our function. We have assumed that the function is a linear combination of parameters and feature functions. Now we should ask ourselves the following question. What conditions must be satisfied to achieve a simple mathematical expression? Well, I think you would agree that mathematical expressions appear simpler if they contain fewer terms. If some of the parameters w were 0, the corresponding terms would vanish and the mathematical expression would simplify. Thus, our second objective is that many of the parameters w are 0. Or, because we want to formulate a minimization problem, let's frame it this way. We want to find parameters w such that the number of non-zero parameters is minimized. This is, by the way, the reason why this method is called sparse regression. In mathematics, a vector or matrix is called sparse if it has a lot of zero entries. In our case, we want the parameters w to be sparse. To quantify the number of non-zero parameters mathematically, we can introduce a function that counts the number of non-zero parameters w. We define the function lcount as the sum of L of w, where L is a function that checks whether a parameter is non-zero. If the parameter is 0, then L is 0, and if the parameter is non-zero, then L is 1. Let's visualize the function lcount for an example with two parameters, to better understand that this function is really counting the number of non-zero parameters. If both parameters are 0, then lcount must be 0. If one of the parameters is 0 and the other is not, then lcount must be 1. And finally, if both parameters are non-zero, then lcount must be 2. So we can see that lcount indeed counts the number of non-zero parameters w. This means that we can reformulate our second objective. We want to find parameters w such that the counting function lcount is minimized. Finally, we have formulated both our objectives in a mathematically sound language. We could now compute the parameters w in a way that both the loss function ldata and the counting function lcount are minimized simultaneously. But unfortunately, there is a catch. Remember that I said the counting function is discontinuous? Whenever a parameter changes from being 0 to a small but non-zero value, the counting function jumps. In theory this is not a problem, but in practice it is very computationally expensive to minimize discontinuous functions. To alleviate this problem, we get creative and formulate a continuous function that approximates the discontinuous counting function. We define the function lp as the sum of the absolute values of the parameters w to the power of p, where p can take values between 0 and 1. Let's visualize this. First, let's consider the counting function for just one parameter w1. It takes the value 0 if the parameter is 0, and otherwise it's 1. Next, let's illustrate the function lp for p equals 1. For decreasing values of p, the function lp converges to the counting function. Thus, lp can be interpreted as a continuous approximation of the counting function. We can also visualize this considering two parameters. Here you can see the counting function and the function lp for p equals 1. Again, for decreasing values of p, the function lp converges to the counting function. But in contrast to the counting function, the function lp is continuous, which means that it is easier to minimize it. Please note that in practice we usually assume that p equals 1, for which the problem gets even easier to minimize because then lp is a convex function and we can use methods from the well-established field of convex optimization to approach the problem. I admit that for p equals 1 the function lp doesn't really look like the counting function anymore, but we will see later that it anyway serves our purposes quite well. Finally, we can reformulate our second objective once more. Instead of the counting function, we want the function lp for p equals 1 to be minimized. In general, the functions ldata and l1 have different minima, which means that we cannot find parameters w such that both ldata and l1 are minimized. However, we can try to compute the parameters in a way that both ldata and l1 are small. To do this, we simply add the two functions together to define a new loss function L_total. And by minimizing L_total, we make sure that both L_data and L1 are small. In this way, we try to find a compromise between minimizing L_data and L1. As we want to find a compromise between minimizing L_data and L1, it makes sense to scale one of the contributions by a positive multiplier alpha. By adjusting this multiplier, we can determine whether we want to pay more attention to L_data or to L1. If alpha is, for example, 0, then we are just minimizing L_data, and for increasing values of alpha, we put more and more attention to the function L1, and thus we will get more and more sparse solutions. Let me give you an example for just one parameter w1, where I assume that L_data is a simple quadratic function that has its minimum at w1 equals 1. As we increase alpha, the influence of L1 increases, in a way that the minimum of L_total gets smaller and smaller until it is exactly 0. This is why increasing alpha increases the sparsity of W. Let's return to our regression example with two parameters. Here you can see the loss function L_total for alpha equals 0. As we increase alpha, the influence of L1 increases until the minimum of L_total is at W1 and W2 equals 0. Of course, we do not want to increase alpha until all parameters are 0. We must tweak alpha to find a good compromise. Here I'm showing L_total for the same example in the vicinity of the minimum. If we increase alpha just a little bit to 0.01, we will see that the minimum of L_total is shifted in a way that one of the parameters is 0, while the other parameter remains non-zero. If we plot the resulting function f and write down its mathematical expression, we realize that with this function we accomplish both of our objectives. There is a small discrepancy between the function and the data, and the mathematical expression of the function is simple. As I said, we usually consider much more than just 2 features in practice. Here's an example considering 6 features. This is the result if we apply the conventional regression. All parameters are non-zero. Using sparse regression with alpha equals 0.01, all but one of the parameters are 0, and thus we again obtain a simple function f that aligns well with the data. Notice at this point that the graphs of the functions that we obtained from conventional regression and from sparse regression do not deviate much, but their mathematical expressions look very different. Until now we haven't talked about how the loss function L_total can be minimized. Minimizing L_total is not as straightforward as minimizing just L_data. This is because the term L1 is not smooth. For some parameters W, the derivative of L1 is not defined. Therefore, we cannot compute the derivative of L_total and set it to 0 as we have done for the conventional regression problem. So this seems to be quite difficult to minimize, doesn't it? Well, if you ask the friendly mathematician in your neighborhood, he or she will tell you that there are actually some very efficient computer algorithms to solve such problems. Especially because L_total is convex and in general it is not so difficult to minimize convex functions. And we are lucky, such algorithms are already implemented in most software libraries for scientific computing. If you want to get your hands dirty, check out the description of this video, where I will add a link to the Python code for all the examples that I have shown here. The example that we considered here was fairly theoretical. Next, I would like to show you a more practical example from my own field of research, which is the study of the mechanical behavior of matter. I will not dive into details here because likely this is not your specific background. I just want to demonstrate that sparse regression can have very practical applications. So try to focus on the bigger picture and don't get worried too much about technical details. Let's revisit the example that I mentioned at the very beginning of the video. Richard von Mises and Henry Tresca are famous for their contributions to the field of solid mechanics. Specifically, they have studied how solid materials deform upon external loading. For many solid materials, if the mechanical stress in the material reaches a certain state, the material exhibits a sudden change in resistance and it undergoes permanent or so-called plastic deformations. Von Mises and Tresca proposed different mathematical equations that describe exactly this phenomenon. In these equations, sigma 1, sigma 2 and sigma 3 are variables that describe the state of mechanical stress for a material in 3 dimensions. The equations describe for which state of stress the material starts to deform plastically. Specifically, the equations describe surfaces in the stress space. If a material is subjective to external loading, the state of stress in the material changes. As soon as the state of stress reaches the surface, the material starts to deform plastically. Now, you might be wondering, why do the equations proposed by von Mises and Tresca and the associated surfaces in the stress space look so different? Why couldn't they agree on just one equation? Well, the problem is that von Mises' equation is more accurate for describing some materials, while Tresca's equation is more accurate for others. And it gets worse. For certain materials, none of the two equations is quite accurate, and we have to develop entirely new equations. And please note at this point that the issue of having multiple equations for describing the same phenomenon is not unique to solid mechanics. It occurs in many scientific disciplines. My colleagues and I have proposed a method based on sparse regression to automate the process of finding the right equation to describe the behavior of materials. Without going too much into details, the method works as follows. We conduct an experiment in which we deform a specimen of a certain material, and we use a camera system to record the deformations of the specimen during the experiment. Afterwards, we solve a sparse regression problem to automatically derive which equation is best to mathematically describe the deformation of the material. In this way, the sparse regression algorithm automatically finds out whether the equation proposed by von Mises or the equation proposed by Tresca is better suited to describe the material behavior. And if neither of the equations is appropriate, the method automatically proposes entirely new equations. Of course, I don't expect you to understand all the details of this example. I just wanted to show this example to demonstrate that sparse regression can find very practical applications. You have just seen one of them, but the same idea can be applied to various problems in different scientific disciplines. Anyways, if you are interested in learning more about our research, I will add a link to one of our papers in the description of the video. Let's conclude. Sparse regression is a powerful tool for automatically deriving simple functions to describe complex datasets. It is extremely efficient at selecting the most relevant features from a large set of potential candidates. And it is very reliable. While it is very likely that different scientists propose different equations to describe a phenomenon, computer algorithms consistently yield the same result. However, sparse regression also has some limitations. We have learned how sparse regression can be used to derive a simple function to describe the relationship between a cause and an effect. To do this, we have assumed that the unknown function can be expressed as a linear combination of parameters and feature functions. But there may be other functions that are better suited to describe the data, but that cannot be expressed as a linear combination of parameters and feature functions. For example, functions that have parameters in the exponent. In its conventional form, sparse regression is not capable of deriving such functions. Further, we have assumed that we already know the cause and the effect. We assumed that y depends on x and just on x. But in reality, one effect may have several different causes, and it is not straightforward to determine which cause or combination of causes the unknown function should be dependent on. Finally, the main idea of sparse regression is to find simple mathematical expressions for describing complex phenomena. But who guarantees that every phenomenon can be described by a simple equation? Maybe sometimes the world around us is too complex to be described by a simple equation. All these limitations indicate that we are still far away from fully automating the process of deriving equations. But what do you think? Will algorithms like sparse regression substitute the work of scientists in the future? Write it in the comments. And as always, if you liked the video, consider sharing it with your friends. Stay tuned, bye!